Good morning.
Good morning.
Landon's here, Ben is here, David's here, Hannah's here. And I get to see Hannah's face. All right. This is it. Time to make the final push. So, what does that look like? So this is a legit final, but fortunately in this class, as I think I mentioned yesterday, there's kind of a building aspect to all of this in the sense that we aren't doing brand new things we haven't seen before. And in a sense, we've been practicing it the whole time. So this is a pretty accurate review in terms of what you're going to see on the test. So let's just have a quick first look. Ultimately, you have two options as you leave differential equations for how to solve these guys. One of them is undetermined coefficients. Other is using Laplace transform. I probably will ask you to use one or the other. So in these problems, I said, why don't you do it both ways just to practice? And again, what you're seeing here is in those three problems anyway, is kind of the worst thing we solved, a second order differential equation, where in 2, it's equal to a polynomial, and 3, it's equal to an exponent, and 4, a trig expression. But then we also solve first order differential equations. And you have the same options for those. You can take guesses, or you can take Laplace transforms of both sides, or if they're linear, then you could use kind of the mu technique. You'll have access to all the notes we've had in the past, which would be, the list of like how mu works and so forth, just as something to kind of guide your mind by. You'll certainly have the Laplace transform table. Probably won't ask you on what I'm showing you here is what I'm going to be asking you on the test. I'm not going to, as I did in previous tests, I'm not going to ask you to make any of the Laplace transform table, which, it'd be fair game, but I'm not going to do that. So you should be able to solve first and second order differential equations with some reasonable skill. And then we really did 2 applications. So rehit these, the concept of a spring, anything that kind of bounces. That's one of the wonderful, as you leave this class, it's one of the things that this models so well. And again, we have an equation for that with damping coefficient, spring constant, and so forth, mass, but that'll be on the note sheet as well. But 5 and 6 are both modeling based. And then most recently, and essentially I haven't had a test over question 6. So I'd be, I don't know, for today, I'd be most worried about 5 and 6. If I was you, I might run through and practice 1 through 4. But if you're, I don't know, tracking really strong, you might kind of, maybe you feel like I don't really need to practice 1 through 4. But I would think you might for number 5 and 6. And I'm particularly concerned about 6 only because it's, something we only did 1 time through. You had a question in your assignment. We did 1 in class. But the ability to write, in this case, a system of differential equations to model the flow, since there's kind of an X equation and a Y equation, and because all we know is rates of change, it's going to end up as being a differential equation. And then I'm kind of interested in if you can kind of apply everything we did in chapter 5 to this problem. In other words, can you write your own system? And then what we just studied yesterday, question B, can you find the critical point on the phase plane of this? That's kind of cool. Maybe, by the way, you saw this, but I sent you guys an email yesterday because after I got off, I spent a few minutes Googling phase planes and then regretted not doing that before class sometime because there's been an improvement since the last time I taught this class, and I found a whole bunch of them that did a really good job really quickly and already had the arrows on them. So the idea that, you're going to get for part A, and we can do this together in a little bit if you want, you're going to get some X prime equation with maybe X's and Y's on this side, and you're going to get a Y prime equation with X's and Y's and maybe numbers on this side of the equation. And the fact that if you set those two things equal to 0, that's where the critical points come from. And what's kind of cool in this problem is, what's the context of that? Like, why is that a critical point? Why? And in this case, I said critical point because I'm sort of telling you in advance there's only one. Like, what is that? Why is it critical and so forth? And then, of course, can you actually solve that system of equations? So for C, you have a couple methods for that now, maybe substitution, but that kind of operator method in 5.2. That I think was the strongest method, like the one that would make your life the easiest. But basically, if you can do this, do these things, you'll ace this test. So, and then I guess the only other thing I want to remind you of, let's see, do I still have note sheets on here? Try to close it this one. I guess the only other thing I'd like you to kind of leave, I don't know if the right word is having memorized, but if I take a look at that spring equation right there, MBK. Oops. Just considering this first problem. Because I want this to be something you don't have to memorize, otherwise you're just not going to know it later on, which is kind of cool. But that's basically the spring equation. Since your external force is gravity, gravity is a force. This is Newton's, I think, first law. Force is mass times acceleration. That's the backbone of a ton of amazing truth in physics and engineering. But acceleration of gravity is, so this is mass times acceleration. It's just G there for gravity instead of just generic acceleration. But the point is if you put a weight down on a spring and then it of course pulls it down, and then you look for it to stop, does it make sense if it stops that Y double prime is equal to 0? Since there's no acceleration, the thing isn't moving, and there's no speed, it's not moving either. And so it's not something new, it's not something to get to memorize, it's just the spring equation. So that's my ability to find K, is to say, all right, that thing pulled it down a length of 4 meters. So that's what resulted. And it weighed 40 kilograms. And I know what gravity is, I know what the acceleration of gravity is. And so those are 3 of the 4 unknowns in this remaining algebra equation. So you can actually figure out the spring constant yourself. So both, there's nothing that you have to memorize to figure that out. It's the same equation you've been working with. But then also in the real world, just the fact that you can actually determine the spring constant of something, even if you bought a spring and it was labeled on it, that probably wouldn't be as good as taking some of your own measurements, because every spring wouldn't be the same. So anyway, I just kind of want to remind you of that because it's been a while. But with that, you are free to take off and do what you want with this. So my advice would be, just because it's kind of fresh, I'd start with number 6, because you probably feel the least good about that. We just, like I said, not much of it.
I agree.
Why don't you, I don't want to just do it for you. I'd rather see you I'd rather you kind of, maybe we'll do this, like tackle A, try to write your system of equations right now. And I'll try to give you enough time to either run out of brain or, okay, I think I have it. And then I'll do that part, but let's get A right before we continue to find critical points and so forth, just so that we're proceeding correctly. But that'd probably be a smart use of your time. But again, this isn't an assignment, so do this if you want to. And in the writing of your equation, notice the unit for X of T. X of T is ounces of chlorine. It's not a speed. It's not liquid. It's a weight of chlorine. Y of T is ounces of chlorine.
Yeah, so Doug, I had a question about this kind of problem in general.
Yeah, fire away.
So when I was doing the homework problem, there was, the tank problem. What I ended up doing was setting it up in such a way that I just found the differential equation for X and Y separately, and then just work through the same process for each one. But is there a way that I can take the answer for one, plug it back into the other somehow, and maybe have a slightly faster process for finding the other one? Or
yeah, absolutely. Yeah, you definitely do not. And by the way, I will definitely give you a question like this on the test. I probably won't even ask you for both. Like I'll just ask you to find one, like find X of T and then be done. Because you're right, you just repeated the same process. But yeah, there's a way faster way. So yeah, we'll get to that. Good observation. So it's important to notice that the tanks are in equilibrium in terms of liquid, like there's tank X is staying at 200 gallons and tank Y is staying at 100 gallons because there's 7 gallons going in and 7 gallons going out in the 200-gallon tank, and there's 13 in, 13 out. So liquid wise, there is no change at all. And so that's why we're concerned with chlorine change. And you may notice there's a lot more chlorine and a lot less liquid in the Y tank, which means this is kind of high concentration. Whereas the other tank only has 180 ounces, but then it's 200 gallons. And so it's like more water, less and less chlorine. So this is kind of low concentration. But then of course, when you turn the pumps on, who knows what's going to happen. I'll give you a minute more and then I'll write out what I think is the answer.
And ounce here, that's a measure of like weight, right? Like mass.
Say that again.
So ounces here, that's not fluid ounces. Those are like ounces in a pound, right?
That's actually a good question. Let's see, do we know that for sure? I don't think we know. Like it could be liquid ounces or it could be weight ounces.
Okay, it doesn't matter then.
Yeah.
I was like, volume per volume. I don't know. It just felt weird.
Well,
But I guess it could potentially be like the amount of a liquid dissolved in another liquid or something.
well, and realistically, like this unit over here, that you can't really just say 8 gallons a minute. It's sort of assumed 8 gallons of liquid per minute and 3 ounces of chlorine per gallon. Like you have to assume that's what that means. But that should be, maybe could be argued that should be stated. So let's see. The rate of change. So if I say dx dt, or just x prime for short, the rate of change of the chlorine in the X tank is equal to the rate in minus the rate out. Well, notice you have 7 gallons of liquid per minute coming in, but that's not chlorine. I need that to be dx dt is ounces per minute of chlorine. So I need this to be ounces per minute of chlorine. Well, it's not. It's 7 gallons of liquid per minute right now coming in. And how much chlorine is in it? Well, I can't say 280 ounces per 100 gallons. Although that would be nice label-wise, because notice it's ounces per minute now of chlorine. The reason I can't say that is that's only the amount of chlorine at the start, but it's going to change because I have liquid going in and out of that tank. And so instead of 280, well, that's the definition of why is the ounces of chlorine in the tank. It's changing. It's calculus. So it starts at 280, but it isn't going to stay 280. So awesome. There's Y ounces in there in 100 gallons. It's going to stay 100 gallons. So I don't have to say 100 plus T or 100 minus T or 100 minus 2T or any of those things. But notice that's ounces per minute of chlorine, which is what it needs to be because that's what dx dt means. But then you also have 7 gallons per minute going out. Notice I just grouped them together. It doesn't matter that there's 5 and 2, they're just going out. If there'd been one tank, one pipe going out at 7, it'd be the same exact thing. Again, that's liquid though, but how much of that is chlorine? Well, same as before, except for we're in the X tank. That'd be X ounces from that tank per, not 100, but 200 gallons in this tank. So gallons cancel. So all the units are ounces per minute. dx dt is ounces per minute. Rate in ounces per minute, rate out ounces per minute. So to clean that mess up, I could say 7y over 100 or 0.07 over a 0.07 y if I wanted to, just to have no fractions, and then minus 7x over 200. Divide the top and bottom by 2, that's 3.5, so it'd be 0.035x. And I know the units are okay, so I'm leaving them off. And so there's my rate of change in my X tank. Similarly for Y, feels like we should change colors because we can. The rate of change in the Y tank, in other words, Y prime for short, is rate in minus rate out. But notice that one actually has a rate coming in, like it's being fed. The other tank kind of was not being fed. This one is actually being fed. And again, notice the units. It's 8 gallons per minute of liquid coming in times 3 ounces per gallon of chlorine. And so 24 ounces per minute. That's a lot of chlorine coming into the tank. But what else do we have coming into the tank? Well, we've got this 5 over here. So plus 5 gallons per minute of liquid, and it, as before, is X ounces per 200 gallons. And so those are both rates in, those are both pipes coming into the tank. And then finally there's stuff going out of it. Again, there's a total of 13 going out of it. It doesn't really matter that there's 7 and 6. And so I'm going to say 13 gallons per minute. And that's the Y tank. So that's Y ounces per 100 gallons. And so the gallons cancel. And so what does that equation really look like? Y prime equals 24 in plus 5x over 200, which is 0.025x, minus 13 over 100, which is 0.13y. So did you get those two equations? And either way, more importantly, do you agree? Are you feeling it?
Is this supposed to be plus 0.025x?
Yes.
Okay, just making sure.
That was a plus. Thank you. I was actually just about to check my answers. I'll do that. So then, can you apply to this what you learned yesterday? So right off the bat, what's kind of cool is you could actually draw a phase plane for this. In other words, the direction of travel. Which we'll get to in just a second. But, you know, are there really some really important points on this graph? Some points that are kind of more important than others, if you will. Critical points, we called them yesterday. And as I said, I hinted that there's only one on this particular one. And those are found when both are equal to 0. Again, when you stare at that problem right there, you should say there's thousands of X's and Y's that make that equal to 0. But not only does that have to be true, this also has to be true. And is this okay with you if I do this? Since this is equal to, I kind of want these to look the same. So I'm going to leave 24 over here, and then I'm going to move all the other stuff to the other side. So 0.13 wide, add that to the other side, and then minus 0.2025x And I'm doing that because now that they're lined up like this, I can see that it'd be, I don't know, easy for me to solve these. And I'm just going to do it by hand. It'd be easier to stick these into the matrix, but I'm just going to do it by hand. It's not that hard.
So would that be a -24?
Maybe. No, I left it on this side and then I added that 13 to the other side.
Oh, gotcha. Okay.
Subtracted that 0.025. So then for no good reason, I'm just going to get rid of the y values. So I'm going to multiply by each other, which is, by the way, how your matrix and in linear algebra works. I just take whatever in front of the y and multiply it by the other equation. And then that means the two y values are going to be the same. And, you know, it's nice if you pick one of them to be negative. Therefore, then when you go back to kind of do your math, you can add those two equations together. So, and the other thing you might do is like multiply both sides by 1,000. Like I don't like decimals, maybe you say. And so before I even started this, I could have multiplied both sides by 100 or by 1,000 or something and not had such weird decimals, but. So this is a little dangerous because I'm doing this kind of all at once, but I got negative 0.0063x. I got 0y. That was the whole reason I did this. Actually, that's not true. I see that I typed something wrong. Should have got positive 0.0028. So again, that's the downside of leaving things such a mess. In terms of small decimals, great. And then 0.13 times 0, of course, is still 0. 0.07 times 24 is actually 1.68. So apparently if I take 1.68 and divide by 0.0028, I get x is 600. And if I take that 600 and put it back in up here, and again, you can see why the matrix is such a cool feature because, you know, it's dangerous. There's lots of decimal points and zeros and negatives and all kinds of dumb stuff I could do here, but if I didn't blow it, I got y is 3,000 up there. And now just to do a quick double check, I'm going to type 0.13y, 0.13 times 3,000, and then subtract 0.025 times 600. And of course, I'm just sort of hoping that when I hit equals, I get 24, and I didn't. So that's good because that means I screwed up somewhere and I got to go find it. So as I said, that's why the matrix is such a great way to do this, because I'm sitting there pointing out all the mistakes I could make and I managed to make some stupid mistake. So great, irritating. Zero, 3, 5 times 600 equals 0.07. Yeah, so I typed, instead of 0.035, I typed 0.35. Then I want to think.
That's so funny. I was gonna say maybe you made a sign error on the 0.35.
Well, I put negative 0.35 instead of 0. Like I left that 0 off right here. I left that 0 off. Again, there's just so many dumb things you could do. So now I'm back checking it at the bottom again. 0.13 times a y of 600 minus 0.025 times an x of 300. Again, I'm crossing my fingers and I still got it wrong. This is actually getting a little embarrassing now. So I still didn't get 24. I got 70.5 over here. So now I'm looking, thinking,
I got 24.
when you checked it.
Yeah, when I put
Oh,
300 and 600 in the bottom equation.
got it. I was rechecking everything. You said you got that. And then, again, just to increase my embarrassment and stupidity, what did I do to check this? I took 600, which is X, and I plugged it in right here for Y. So, okay, whatever. And embarrassment. So that's my critical point. So in other words, that point's special. Now, again, what did we learn yesterday? We learned that right around that point, we saw, well, actually, we didn't really learn this yesterday, but we saw that sometimes this was the case. There was like, if you look really close, the arrows around it look kind of like that. So maybe it's like a swirling pattern. So let's back up to, here, and then just for the heck of it, let's go put that into a graphing utility of some sort. So I'm pulling up, I'll share a screen with you in just a second on that. I'm quickly pulling up the phase plane plotter that I found yesterday. Stop sharing, start sharing. So I sent this to you in an email, and I also posted this yesterday. This is kind of a neat one. Notice it has arrows already in it, and there's some other things about it I'll show you in just a second that are pretty cool. So link to it, control click. And you got to pay attention because notice that says X is first. Unfortunately, I wrote X first, so I had 0.07Y.
We see your desktop.
You see my desktop. There we go. Thank you. User error yet again. So I don't know if that's big enough for you to see, but I typed my X prime equation in there, double checking it. And then my Y prime equation was 24, and then plus 0.025X minus 0.13Y minus 0.13Y. And I get a generic window of -5 to 5, an arrow length of 15, a number of arrows of 20, and then it says variable arrow length and whatever. I'm not paying attention to that. I mentioned this in my email to you yesterday, but I'd forgotten it now, but it says, notice the direction field solver knows about trig, logs, exponentials, but multiplication has to be explicitly entered. So you can't say 0.07Y. You got to say 0.07 times Y times X. Read the directions. So notice every arrow kind of shows that it's kind of on the increase, if you will. But of course, remember my ordered pair was out there at 600, 300. So I've got to change my window to be a whole lot bigger. So let's see. What am I going to do about that? Minimum X. I think I'll leave it at that and take it out to, I don't know, 800. Let's do the same thing with Y just to keep it square. Graph.
You change your minimum Y, not your maximum X.
Oh boy. It's trying to graph it now. Yeah, once again, got to read the directions. So -5 to 800, -5 to 800. Okay, that's kind of fun. So one thing that's just kind of cool about this, like that's pretty decent, like the arrow length and the number of arrows is pretty decent. And you certainly can fool around with that. I'll put 30 of them on there and notice that's kind of what happens. What does variable arrow length do? Don't forget that, and in this case, I'm going to have to decrease the number of arrows to even see what's happening there. Remember, the arrow length is actually literally a vector that tells you the velocity. And so sometimes, like over here, you can actually see there's some reasonably short ones. But for the most part, these are really big numbers. I mean, this thing is changing very rapidly. And so remember, it's actually deceptive if you say the arrow length, and this is the way most of these work, the arrow length is because those are not all the same length. Now, what do you notice about the point that we found, which was 600, 300? First of all, can you find that? Notice the units across the bottom are sort of wonky and they're such big numbers that they kind of run into each other. But let's see, what do we got here? 627. You can't even read it. They're so, at least on this side. But I think I'm seeing 627 right there, but I'm 627. 667, I don't know, right in here. And the Y is 300. I can't read that either. Oh, there's 345. So there's 345. So that must be 305 right there, but I can't see that very well. I don't know if there's a way to fix that. But it's actually kind of right here. What do you notice about all the arrows if you kind of go here? Well, they're actually all pointing that way. They're all kind of pointing there. In other words, that's where everything is going. That's what's kind of interesting. They're all heading to that point. So what this is operating like is this point in space is kind of like a black hole. Like no matter where you drop in, if you drop in right here, you start following these lines and you head to that spot. If you drop in up here, you come down curve and you head to that spot. So this point is behaving like a black hole. Now, why would that be? Why would that be the case with what we are working on?
Because it kind of tends toward an equilibrium concentration.
That's exactly right. In the end, if you turn these pumps on and go long enough, then you're going to have an equilibrium that's reached, and that's where it's going, no matter what you start with. Notice in our case, we had these starting values, and that would have put. And the one thing I would love to have done on that other graph is being able to kind of put in our initial conditions so that because we're following a particular path, right? We're not following all those paths, but the reality of that phase plane we just saw is all the paths, no matter where you start, are going to end up at some equilibrium. And so let's solve this now, and that'll be a kind of a neat part of the solution to this that I think will help you understand this even a little bit better. So, you know, for the test, it's like, do you have to understand that equilibrium point? Do you have to, or that critical point? Do you have to understand what it is or why it's important or whatever? No, you just have to be able to get it. So in our case, what was actually happening is not what we might have saw yesterday, but it was kind of like no matter where you were, you're going toward that spot. So again, it acts like a black hole. Everything is gravitationally pulling toward that, no matter where we started. So lastly then, let's go try to solve this thing. Can you actually find functions for those? Can you solve them? And just to kick you off in the right direction, if you want this to be easy for yourself, we learned that there's this cool thing called operator form, where instead of x prime, you write dx, so that now the two x's can be collected together, since if I added the 0.035 x to the other side, and I think I'll even subtract the 0.07 y to the other side, Now those two x's can be thought of as both being an x instead of one's x prime and one's x, so I can't do anything with them. Now we said that I could factor that x out, leaving d plus 0.035, so that now there's not two x's but one. And there wasn't a y prime, so that's kind of the operator form way to write our x prime equation. Do you see the beauty of that? And then similarly for our second equation, notice I'm trying to set it all up so that it's x's and then y's and then equals numbers. So I want to do the same thing with the second equation. So I'm going to get all the x's and y's on the other side. So I've got a negative 0.025x. If I subtract it to the left side, there's already a y prime over there, which we're calling dy now. And then if I move the 0.13y over to that side and leave the 24 on the right side of the equal sign, again, this accomplished the fact that I don't have y primes and y's now, I just have y's. And therefore I can factor y out and leave the operation of derivative for later. There's no such thing as d by itself. You can't just say derivative, just like square root. If somebody said, what's the square root? You'd say, well, square root of what? Like you have to operate on something. You have to operate that. That's an operation, and I have to perform it on something just like a derivative. So the fact that it's distributed to this y means it's really just derivative. So it's no different, it's just a derivative. So because of that nifty little trick, then you can actually solve that system of equations in the same way that we just did up here. I said, let's multiply by 0.13 and 0.07, and we got rid of the y's. And so it doesn't matter which one I pick to get rid of. I'm going to take the same exact approach. So let's see, for no good reason, I think I'm going to get rid of the y values. So I'm going to look at this and say, well, that's a d plus 0.13. Well, then this needs a d plus 0.13 multiplied by it so that it matches. And then this is a 0.07. So that means this needs to be multiplied through by 0.07. And then the y terms will drop out because they'll be identical. And again, do I want to add them or subtract them? I got to be a little careful with this. So I'm going to have a d plus 0.13 and a negative 0.07 on top in the green equation. And I'm going to have a d plus 0.13 and a positive 0.07. So this negative being here right now will take care of the fact that one is negative, and I don't have to make one of them negative. It already was negative. So just to write out what I've got x times d plus 0.035, and now also times d plus 0.13. And then I've got minus 0.07 times d plus 0.13, and that's all times y. And then fortunately, on the other side, it's equal to 0. So when I multiply that, it just stays 0. And then look what happens with x. I've got x times negative 0.025, and now times 0.07. And I've got plus 0.07 times d plus 0.13 times y, which is good because I can see now that these are just going to cancel. They're exactly the same, which is the whole point of this. And then times 0.07 times, I suppose that looks like a multiplication. It looks like an x, so I'll use a dot. So now I can add these. So. And again, with all these decimals, I'm very much regretting right now not starting by multiplying by 100 or maybe multiplying by 1,000, because now I'm going to have to multiply 0.035 times 0.13, and I'm going to get these just ridiculously teeny decimals, which just seems dumb. But it's not that I can't do it. So if I add these, I'll have x on top. I have d plus 0.035 times d plus 0.13. I'm going to need to multiply that out. D times d. And then for my middle term, I'm going to have 0.035d plus 0.135d, which is 0.165d. And then finally, stupidly, 0.035 times 0.13. I'm going to have some ridiculous decimal. And then I'm adding it to this mess. And there's no d's in that, unfortunately. So when I multiply those, I just get a number, and it's negative, and it's 0.00175. And then that equals whatever 0.07 times 24 is, which is 1.68. And so, of course, the good thing there is I have an equation with only x's. And if I distribute this back out, notice you have d squared times x, which really just means x double prime, means take the derivative of x twice, plus 0.165 times dx, or 0.165 times the derivative of x. And then x times this number minus another x times that number. I end up with 0.0028 just times x, and that still equals 1.68. And so for the first time, I realized, oh, that dropped into a second order differential equation, which I can now solve. But wow, that was a lot of work to produce, if you will, one of these, well, second order differential equations that we've been solving this whole term. And so it's kind of weird, like that was a whole bunch of work, and yet now I'm just ready to, I guess, get started, you might say. So this is good review for us. I'll just ask this rhetorically, but are you a person now who says I'm going to take the Laplace transform of both sides of that, or are you just the person that says I'm going to take a guess? I'm going to choose to take a guess. First, I'm going to get the homogeneous equation where this is all equal to 0. And my auxiliary equation is r squared plus 0.165 r plus 0.0028. And I would definitely be multiplying by something to change it now, except I have a graphing calculator program that can tell me the quadratic formula answer to that. And since it's homogeneous, that means this is equal to 0. So if I throw in 1 and 0.165 and 0.0028 into this, I got two values for r. R is approximately negative 0.019 and negative 0.1457. So I'll call it 146. And so y1 is equal to c1e to one of those plus c2 times the other one of those. So there's part of my equation.
Real quick, where did you get the 0.0028? Did you add 0.00175 to 0.00455?
Yeah, I mean, this was negative and this
Oh.
was positive. So
Okay.
I think I went 0.00455 minus 0.00175, which of course I could have screwed up.
No, I added them. I messed up.
So there's that. And then there's my second, and this is kind of an odd guess. Like what do you guess for this if you have a constant on the other side? What is my equation equal to? And by the way, I probably should be calling these things not so much y1 and y2. I should, I guess, be calling them x1 and x2, right? Because we're finding the x equation here, not the y equation. But the answer to that question is there's nothing over there. It's just a c, like a constant. In other words, x is going to be an equation, and all it has to be is a constant because all it needs to produce is a constant. So then again, I plug it back in and I say, okay, well, I got to plug in its derivative, which is nothing, and so is its second derivative, so that's nice. So then I'm basically just plugging in c right there, and so that results in 0.0028 times c being equal to 1.68. 1.68 divided by 0.0028 turns out to be, not surprisingly, 600. So now my x general equation is both of those added together. When I say not surprisingly, I'm saying that because didn't we see a second ago that x was equal to 600? Why was that a critical point? Because what happens to this equation as, let's go ahead and write this calculus correct. What is the limit of x of g as t goes to infinity? Since this is negative, then this expression could be thought of as moving to the bottom. So it'd be e to the 0.019t on the bottom. Well, as t goes to infinity, e to that number is going to get huge. So you have c over a huge number, which goes to 0. So this goes to 0, this goes to 0. Therefore, this thing's limit is 600. That's why that was a critical point, because that's its destiny. If you turn the pump on and just let it roll, you're going to have 600. Let's see, what was x again? Ounces. You're going to have 600 ounces of chlorine in the tank. Like that's where that's heading. So no matter where you started on that phase plane a while ago, they were all pointing toward an x of 600. So that's just kind of cool to note. Now, we're not done because we haven't figured out our particular equation for g, and I've got to go back to this problem to determine what were the initial conditions. X of 0 was 180, y of 0 was 280. And I'm thinking to myself, you know, like, how is this one going to do me any good? Because I don't have a y equation. But at least I don't know, maybe I'll put that off till later, but at least I can start with this one. At time 0, I'm supposed to have 180. Okay, well, that means x is 180. So I'm replacing that side with 180. At time 0, e to the 0 is 1. So you just get c1 there and c2 and 600. So that's true. And I suppose I can subtract 600 from both sides. That's true, except for, unfortunately, it's got 2 unknowns in it. And y of 0 doesn't do me any good here because I don't have a y of 0 equation. Well, I guess I could go back and, you know, start all over and kind of get the y of 0 equation, get the y equation. I have x of g, couldn't I get y of g? But isn't that 2 totally separate equations? And so, you know, it's not like it's going to give me another equation with the same C1 and C2. How do we get out of this mess? How do we make any progress with this? Do I know anything in the past that would help me?
we have an equation for y prime or an x prime originally.
Yeah, I have those equations for x prime and y prime. Do those help me somehow? I mean, my gut reaction is, your gut reaction should be no, they're not going to help you because I didn't know y prime of 0 or x prime of 0. But can they help me? Is there some way they could? I mean, I could certainly take the derivative of x. I mean, this. Does that do me any good?
Just find the y prime of 0. Can you stick the x of 0 into y prime equation? And or x prime, I should say. Doesn't matter.
Yeah, if I have derivatives, in other words, if t equals 0, then I do know the answer to that, right? I know y of 0. I don't know what the equation for y is, but I know that the entire y equation is equal to, what was it, 280? Something like that. So yeah, maybe I could, like maybe that is going to go somewhere. Let's just store this down here. Think about it a little bit. So let's get the x prime equation. So x prime would be equal to, again, I'm just taking a derivative. So that would be derivative of e to the junk. So that means the 0.019 would come down front multiplied by C1, but the e wouldn't change. Same thing's going to happen with the other one. And then, of course, the derivative of 600 is gone. And so that would mean x prime at 0 would be equal to negative 0.019 C1, again, because e to the 0 is 1, minus 0.146 C2. And so that would be terrific if somehow I was told the initial speed, right? The initial change, but I wasn't told that. So does that equation we brought down help us to figure that out? I mean, isn't, if I plug in 0 for t, then isn't this automatically y evaluated at 0 minus 0.035 times x evaluated at 0? And so, yeah, don't I actually know that x evaluated at 0, even though I don't even know what the equation is here, was 180, and y evaluated at 0, even though I've never even addressed that problem, is 280. So I actually can use this to find x prime of 0. So 0.07 times 280. Good job, Evel. Minus 0.035 times 180 is actually 13.3. So then I actually have two equations, two unknowns. So if I'm going to use the matrix this time since I've seemed to be failing today. Subtract that over, I get negative 420. The second equation I just got is negative 0.019 C1 minus 0.146 C2 equals what I just figured out this was equal to. So I'm going to stick that into the matrix. I need a 2-row by 3-column matrix. I put in 1, 1, negative 420, negative 0.019, negative 0.146, 13.3. Double check I typed all that right. Second matrix, math reduced row echelon form of matrix A. And I get that C1 is approximately negative 378.110 and so forth. Close enough. C2 is approximately negative 41.89. So now I think of course, there's all kinds of room for me to make some kind of a mistake, but now I actually think I have X particular plugging in these two values. And again, I thoroughly do not trust myself that I didn't make some kind of a math mistake. And so as I often say, you watch me make a number of them today, just make sure your work is clear enough that I can circle your mistakes. I'll try to make these worth enough points that there is room for some mistakes. See, final exam review solutions. I'm just looking really quick at what I posted online to see if I got lucky and got that right. Oh, I did. Rounding is a little different because I must have rounded earlier, but basically that's correct. So to Landon's point, it's like, man, that was a long time ago that how long ago was that? Clear back here. This is where I started. And when I chose to multiply by D plus 0.13, basically I was choosing to get rid of Y. And so I had an X equation, which turned into a second order X equation. And so Landon's question was, is there some way that I could not have to just start all over? And of course, starting over would mean, well, what do I have to do to get rid of X? Well, down here I had a negative 0.025, which maybe I could switch to positive. And up on the top, I had D plus 0.035. And so is there some other way to not have to start over and just redo, what was that, 2 pages of work? So anybody see any place that we could have went to make our life easier? So you have a couple of choices. One of them is right here as just a for instance. Let's see, is that the best one to go to? And one of them is right here. How could that equation help us a whole bunch? To get Y.
Well, you already have your X equation. You just got to find a derivative of it and then plug them all in.
Exactly right. I just found my X equation. Can I just plug it in there? Because remember, X is not in this case, X is not, just the letter X we're used to, like the XY 0.52. X is some equation as a function of T. It's maybe a better idea to write it that way. This is some equation as a function of T. And we just found how big and ugly that really was. And we even found it's a derivative a second ago, right? So couldn't we just plug both of those in and notice that's just Y, which means we're done. We found it. This one is a little yet less useful. Would you agree with that? Because although I could plug my answer in for X here, unfortunately, this has a Y prime in it. So I'd still have a first order differential equation to solve. But yeah, by far, that's the one right there. Plug it into that blue one. Which I don't think I will do just because I want to see if you have questions about other things. But I will at least write it down. I think I already had that one down there for a previous reason, but yeah, that's kind of cool. If I take this and put it right there, and I take its derivative, put it right there, and as I said, we already had its derivative right there. I just have to put C1 and C2 in place of them. I don't have to retake its derivative. I know what C1 and C2 are now, so I can put it in there instead and not have to redo it. But then I could solve for Y. Just for the sake of one final point I want to make, this results in Y particular being about negative 85.2 E to the negative 0.019 T. Notice it's the same equation, except it just has different coefficients in front of it, which might bother you. And then particularly of importance, bam, there's the other equilibrium number. So that's exactly why that was a critical point, is because look, it's on its way to an X of 600 and a Y of 300. So that's kind of cool that the critical point found that fact. And that's why it was critical, because basically if I had told you X of 0 equals 600 and Y of 0 equals 300, you wouldn't have noticed it when you started this problem. But the interesting thing is it would have already been in equilibrium right when you started. So it's like you would have turned the tank on and nothing would have changed. Isn't that kind of interesting? So the phase plane was kind of evidencing a black hole where every initial condition was leading to 600, 300, no matter what you started with. So, of course, that should feel like that would be a good one question final exam, because it involved every single thing we've learned in this class in some respects. Except for we just chose not to use the Laplace transform to solve it. But all right, how's your brain? Let's see. What else would you like to look at? Say 1 and 5 are possibilities. 1 was so long ago, you might think, I don't remember how to do that. Or, of course, the spring is a kind of smacks of being a word problem. So again, we're just reviewing. So if you think you're done, you don't have to stay till the end.
Yeah, could we do 4? Is that what you're pulling up now?
Yeah, I was just resharing the screen. For some reason it seems to be lagging.
So if today is review, what is tomorrow? I came in a few minutes late.
Tomorrow is the test. So you are done after tomorrow. You said 4, Cheyenne?
Yeah.
Which method would you like to look at? Undetermined coefficients or Laplace transforms?
The method A, because I think Laplace transforms we've been working with.
Got it. Mhm. 1 negative 5, 6, 52 sine. Double checking. Oh my gosh, I remembered it. Okay, so the important thing about undetermined coefficients is to recognize that there's 2 answers to this. There is the homogeneous answer. And then there's also the undetermined coefficients answer. So the undetermined coefficients answer is that, hey, look, you have jump times the sine of t. And so your guess for this, for your second equation, this will be our first equation. Your second equation is going to have a sine of 2t, but it's also going to have a cosine of 2t. So that's your educated guess. It's definitely going to work. And homogeneous, since this thing factors to, I'll go ahead and write it really quick. Since the auxiliary equation is equal to r squared minus 5r plus 6 equals 0, and that happens to factor to r minus 3, r minus 2, and then I really don't need the quadratic formula to see that r is 3 and 2. So I'd have C1 e to the 3t plus C2 e to the 2t. So that's going to be my homogeneous answer. And then to proceed with this, again, I want to plug this back in. I want to plug in this equation back up here at the top in order to figure out what would make that be 52 sine of 2t. But I have to plug in y, as I just found, but I also have to plug in y prime and y double prime. So that means I got to get those. So y prime, the derivative of sine is cosine. Derivative of sine of junk is cosine of junk times the derivative of the junk. Derivative of 2t is 2. So that's why there's an extra 2 out front. Similarly with this one, the derivative of cosine of junk is negative sine of junk times the derivative of junk. And now I need a second derivative. Derivative of cosine of junk is negative sine of junk times the derivative of 2, which makes it a 4. And similarly for this one, So there, now I have all my ingredients to plug back in, multiplying by 5s and 6s, and I'm gonna see if I can force it to be 52 sine of 2t, and there's not even a cosine in it. So let's see, I need these, which I'm just going to copy since they aren't multiplied by anything. So there's my y double prime. And then minus 5 of these, so that'd be minus 10a cosine of 2t's. Be careful here, minus 5 minus 2 is plus 10b sine of 2t's. And then finally, plus 6 of these. So plus 6a sine of 2t's, plus 6b sine of 2t's, cosine of 2t's. And somehow I'm supposed to try to get that to equal 52 sine of 2t. And because my guess is using the cheat sheet, I know that I actually needed both sines and cosines for this. And I know there's going to be a value for a and b that make this possible. So I'm saying, okay, well, how am I going to get a 52 sine of 2t? Well, let's look at our sine of 2t's. There's a sine of 2t. And it looks like I screwed something up. Yeah. The derivative of sine is cosine. So I managed to not write that down correctly, but fortunately I caught my own mistake. And I caught it by pattern, just to point this out to you. Doesn't every one of these, shouldn't it have like a sine and then a cosine and then a sine and then a cosine? So I caught that dumb mistake by pattern. So I got lucky. So that means that no longer is a sine. So how am I going to get 52 sine of 2t? Well, here's a sine of 2t. There's a sine of 2t, and there's a sine of 2t. So how am I going to get 52? Well, negative 4a from this one, and plus 10b from this one, and plus 6a from that one better be 52. So notice I got a's and b's, and so yeah, there's all kinds of ways I can get that to be 52. Then I go back and I look at my cosines. Notice there's no cosines on this side. So that means negative 4b plus negative 10a plus 6b better be nothing. So as a side note, what if there had been like a 47 cosine of 2t over here? Does it make sense? My guess would have stayed exactly the same, except for I would have said equals 47 instead of 0. It's not like I have to redo all that. It's just that I happen to have none, 0. So let's see, to rewrite then what I now have, since I can certainly collect these a values together, I have 2a plus 10b equals 52. And then I have negative 10a plus 2b equals 0. And so yeah, 2 equations, 2 unknowns. There is going to be one value for a and b that make both of those true. And so that's why I know my guess was good and that it was going to work. So this seems easier to do in my head. If I multiply this one by 5, I'd have 10a, and 10a and negative 10a is gone. So that'd be 50b plus 2b, it'd be 52b. And then 5 times 52 is 260 plus nothing. So whatever 260 divided by 52 is, that's what I think my value is for a. Hey, it's 5, or b, I mean. So b is 5. If I put b as 5 in here, that'd be 10. And if a was -1, that'd be -10. So I think a is -1, but I'm very much not sure until I go plug it back into this one. 2 times a, that'd be -2 plus 10 times 5 is 50. -2 and 50 is not 52. Good. What mistake did I make? Oh, this was already negative down here. This was already negative, so that a didn't need to be -1. So a just needed to be +1. So does that work? Yeah, because now it's 2 plus 50 is 52. And so again, made another dumb mistake, caught it. So now I know my, now I can kind of go back here and say if a is 1 and b is 5, then I actually know my answer. And so now I'm in a spot where I can, because both of these answers are true, then I can go back and put y1 and y2 together. And again, this is my general equation, because C1, these two constants are still in it. So it's still just a general equation. But notice the sines and cosines aren't general. I actually know those. Probably good practice to put parentheses around those. And so, again, I think this is right, but obviously there's all kinds of math mistakes I could have made. I've shown you ways in Desmos to check this. You, of course, could take the first and second derivative of this and plug the whole thing back in and make sure it all worked. So if all I was asked for is the general solution, then I'm done. If I was given initial conditions, then that would even allow me to find the particular solution. So y of 0 is 4, y prime of 0 is -6. So, cool. T is 0. So when y of 0 is 4, that means y is 4. T, however, is 0. E to the 0 is 1. E to the 0 is 1. The sine of 0 is 0, but the cosine of 0 is not. Cosine of 0 is 1. So when I put 0 in for t here, I get cosine of 0 is 1 times 5. So I get that. So there's kind of my first equation. But unfortunately, for the second one, I've actually got to take the derivative of all this mess. So y general prime would be 3c1 e to the 3t plus 2c2 e to the 2t. Derivative of sine is cosine times the derivative of 2t. And then, of course, the derivative of cosine is going to be sine, which means it's going to disappear, but I'll go ahead and write it anyway. Derivative of cosine is negative sine and also times 2, so that would be -10 sine of 2t. And so our second fact now is y prime is -6 when t is equal to 0. So this is going to go to 1, this is going to go to 1, this is going to go to 1, this is going to go to 0. So that term will be gone. So I end up with 3c1 plus 2c2 plus 2. So there's my two equations, two unknowns, which I hope is easy to solve. Subtract the 5 over to the other side. Subtract 2 over to the other side. And I'm just going to multiply by 2, but I'm going to subtract this time because I think I can survive that. 2c2 minus 3c1 would be minus c1, -2 minus a -8. Ooh, this is why you don't want to subtract. This would be easy to screw up. -2 minus a -8 would be -2 plus 8 or 6. So I think c1 is equal to -6. If that's true, then C2 would have to be 5 because -6 plus 5 would be -1. But of course, what I'm really interested in is, did it work here? 3C1, the -18 plus 10. Oh yeah, it is -8. So I don't think I screwed it up. So now I know C1 and C2. I won't bother to rewrite it, but of course I'm going to just put them back in up here. -6, 5, bam, now I've got a particular solution to this. How's that feel, Cheyenne? Easy?
Yeah, I remember most of the process now, so I just probably have to do a few more review problems.
Yeah, for sure. It's only been 8 weeks. You didn't know any of this existed. Learned a lot of stuff in 8 weeks. Not easy to assimilate that many things into your brain that quickly. Let's see, and you can also ask me more questions if you're just concerned about that, but what else?
Does anybody want to do the spring problem, number 5? Seems like it might be good.
That's polite, but if you want to, that's enough.
Okay, that sounds good.
You count. Whoops, that's not what I wanted to do. Okay, the spring. That's certainly worth reiterating. Crop. So I won't reiterate what I said before, since we saw that the equation, the last part that remained was k times y equals m times g. And we knew that it lengthened 4 meters. So that means y is 4. We knew its mass was 40. And again, this is, I'm certainly not going to trick you on this. Maybe somebody would do this in a physics class, but you know, force is newtons, Newton units are kilogram meters per second squared. That's how mass is measured. That's how acceleration is measured. So the fact that I gave you the weight in kilograms means I was being nice. The fact that I gave you the acceleration of gravity in meters per second squared is being nice. The fact that it lengthened 4 meters is nice. So no tricks in any of this. I'm really just replacing these values. So if I did 40 times 9.8 and divide by 4, which you should be able to do in your head, because 40 divided by 4 is 10, and 10 times 9.8 is 98. So K would be 98. And interestingly, this would need to be, when multiplied by 4 meters, if K was 98 and Y is 4 meters, then you've already got the meters from the 4. So interestingly, the unit for this is kilograms per second squared. I mean, that's one way to write the unit anyway. Or the other way is to say, well, this whole thing is newtons, except for we already had meters. So newtons divided by meters, that's what's in your note sheet. Because then if I multiply that by 4 meters, the meters cancel and it ends up being in newtons, just like the other side is for you physics people. Anyway, cool. Now we know K is 98. We didn't know that before, but we know everything else. So since the equation is mass times y double prime plus b times y prime plus k times y. And in this case, I said use this as the spring's equilibrium position. In other words, when we put the weight on there, the spring came down 4 more meters and then it stopped. And so gravity has now done its work, which means this can be thought of as being equal to 0. Now, it doesn't have to be. You can actually add gravity to it. It's just the equilibrium position would have to be up before you put the 4 meters on it. But since we restarted the problem with that weight on it, and the weight had done its work and now it was just sitting there and not moving, then there isn't any more external forces on it. And so now the spring entirely does the work. Or you could just think of the spring as being sideways. If I put it sideways, then gravity is not pulling on it. And of course, the mass is 40. I can plug that in. I was given the damping coefficient of 15, which I didn't need anyplace else. And we just calculated K to be 98. So I have a second order differential equation to solve. So notice it was pulled down 2 meters and released, which is sort of code for y of 0 equals 2 and y prime of 0 equals 0. The fact that it was released and nothing else was told about how it was released. It's like pulled down and just let go. So its initial speed was nothing. There's also a little bit of a conundrum, like should you say that's -2 because it said it was pulled down? You absolutely can. In my case, I'm kind of ignoring that, and I guess what you could say is I'm treating it as though down is positive, which you have to be a little careful with because it says find the time required in part C to reach its lowest and highest point after release. So it's probably a little safer to say y of 0 was -2 and just treat, positive as up, negative is down. I'm going to go ahead and leave it this way just because it's kind of like, if you do what I just did, you have to think, okay, well, I'm calling down positive. So down is positive. So this is probably not a good way to do this. It's probably not a good idea. I'm actually just curious. I wonder what I did in my note sheet. My solutions to this. You actually did it this way. So that's a little dangerous. Since we solved the other differential equation like this with sort of a guessing technique, then maybe just because it's a good reminder, let's do this with Laplace transforms. So I'm going to Laplace both sides. So I have 40. I'm going to be careful because a lot of people, including myself, make sign mistakes here. So there's a 40 that comes along for the ride. And then what's the Laplace transform of y double prime? Well, again, look this up in your note sheet. Don't screw it up, but I have it memorized. Y double prime, it starts with s squared, and then that takes it down to just the Laplace transform of y. And then it's always minus, and then the s power goes down by 1. And then Laplace is an integral. You take its derivative, which actually means you get your y back again. And then always minus, and then s goes down 1 more. So from s to the second to s to the first, and now s to the 0. So it's actually gone. And then you take another derivative of y. So the pattern that is available on the note sheet is the only reason I can even memorize that. The s's go down, the y's go up in derivative. So there's the Laplace transform of y squared plus 15. And then I do the same thing with the derivative of the Laplace transform of y1. Well, it's only 1, so it starts with s1. And it always starts with the Laplace transform of y. And then I go down 1. It's always negative. I go down 1. So now this is gone. And then this is just y of 0. So that takes care of y prime plus 98. And then the Laplace transform of y is just the Laplace transform of y. There's nothing I can do with that. And that equals 0 because the Laplace transform of 0 is 0. So now I just try to collect all that junk together and not make a dumb mistake. So I'm going to be really careful here. Y of 0 for me is 2. Y prime of 0 is 0. That's really nice. So I'm going to start by collecting all of my Laplace transform of y's together. And I see right here, I have 40s squared of them, and here I have 15s of them. And here I have 98 of them. And I'm of course gratified to see that that is the exact match from what I started with. That's kind of like the auxiliary equation. But then what else is there that I haven't accounted for? Let's see, there's this minus 2s. And that was 0. And then there's a 15 times a minus 2, which is actually minus 30. And that's it. That's all there is. So I can now solve for the Laplace transform of y by first adding 2s plus 30 to the other side, and then by dividing by 40s squared plus 15s plus 98. So then our goal becomes, can I rewrite that to look like something in the Laplace table? And because this is a kind of a practical problem, or if you will, this isn't going to work out real nice. Like this is actually going to be kind of hard. I'm looking at this thinking, maybe that wasn't a good idea.
Hey, Doug. At that a negative 2s, I think it should be negative 80s.
Negative, what should, oh yeah, that's right, isn't it? Didn't I forget to multiply by 40 there? Everyone, so it's not minus 2s, it's minus 80s. Man. Thanks for saving me. Evel. Yeah, I said I was being careful. I was trying to write out and be really careful about doing this, but if I was going to be really careful, I should have taken the time to rewrite this distributed out before I started collecting stuff together. But I didn't screw it up here. I saw that was times 15, right? So it wasn't like I didn't know what I was doing, but that was a mistake. Okay, so do I still have the Laplace table? So the question is, is there something here that I can get this thing to look like? Get rid of all previous marks. So remember, what I would really like is to factor it. That's what I'd really like to happen, so that I could get it to look like a couple of these. In other words, just as an example, if I was able to sum, and I'll erase this because this won't be true, but let's see, there's a 40 and a 98. Like it'd be really awesome if I could factor this to like 20s and 2s, and then 98 is like 49 times 2. If it factored to that, does it make sense? That'd be super wonderful if it did, because then I'd be able to say, oh, this is a couple of E terms. And so that feels like, unlikely, if you will, that would be the case. Anybody know, those are pretty big numbers. This is a realistic problem. Anybody know how I could cheat to factor that?
You could graph it.
Yeah, graph it. If it crossed at, a couple of recognizable places, then that means it actually factors. Interestingly, I'm going to go down this road. Yeah, I think I do. So I am going to graph this. Y equals 40, because maybe I'll get lucky, except for instead of s squared, I'm going to type x squared, 40x squared plus 15.
Is that reducible? It doesn't, looks like it might not be.
Yeah, like maybe 3 goes into all of them, or 5 or 2 or something. Yeah, and if that happened, that would be absolutely a good thing to check.
Well, what I mean is is this going to have zeros? Because it looks like if you do like 15 squared minus 160 times 98, I feel like that might be complex.
That's exactly right. And that's exactly why I want to graph this, to see where it crosses the axis.
right? Because then you could factor out that 40 and then complete the square and do like, see if it's like a sine or a cosine or a,
That's exactly right. So when I graph this, trace, I can't even find it. It's got Y's of like 5,000. Should have graphed this where you could see it. I didn't realize it was such a crazy graph, but when I graphed it, unfortunately, this is what I got. Or fortunately, when I graphed this, I got a graph that looked like this, which means it never hit anywhere here, which means not factorable. So that means my hope of factoring it is sort of no good now. So that stinks. So then what's my choice since this didn't factor? What options do I have left? That means that's out because I'm not going to be able to split it into S-2 and S-3 or something nice like that. Again, the ideal would have been it across it like 4 and 7. Then I would have known, oh, S-7 and S-4. Like I would have been able to factor it without having to sit there guessing at what it might have worked at. But now I'm going to have to look over more at the complete the square business. And of course, because this is a spring, you should have already known it was going to go over here. Well, not for sure. But don't springs tend to want to go, you know, go like that, like they have sine waves, and we said they were dampened by an E. And so it's kind of like, yeah, of course they're going to go. Of course it's going to go over here. So basically I've got to complete the square. I've got to get this thing to look like that. So this is harder. So again, I'm honestly find myself thinking, man, I wish I hadn't done this with Laplace transforms. So, So I have a number of choices right now. Let's do some creative things. Number one, you may have noticed it said S minus A squared. And so that 40 is a problem. So the first thing I could do is divide by 40, the top and the bottom. I'm going to try that first and see if I like that idea. So I'm going to divide by 40. So 80 divided by 40, that's not so bad. 30 divided by 40, that's not real great, but at least it reduces to 3/4. Squared. 15 divided by 40. Let's see, 5 goes into those. That'd be 3/8. Is that right? 3/8. Yeah, 3/8. I don't know if I should be writing that as a fraction or a decimal. 98 divided by 40 isn't going to be any good. So maybe 2.45. I guess I'll just leave it as a decimal for now. So because we're trying to complete the square, what do we wish was right here instead of 2.45? 2.45 isn't gone, but what do we wish was right here? Well, since we need 3/8 to happen, does it make sense this has to be 3/16? Since when I multiplied that out, it would be 3/16 S plus 3/16 S, which would be 6/16, which is 3/8. Well, notice if I finish multiplying this out, I'd have S squared plus 3/8 S plus 3/16 times 3/16, which is whatever that is, 9/16 squared. It's 256. So I actually wish this was 9/256. That's what I wish was there, because then it'd be a perfect square. Can I put that there? Sure, as long as I kind of go back and subtract it. Are you this good at completing the square? Again, notice I'm totally conflicted, like I haven't even decided am I working in decimals or fractions. I am going to take 2.45 minus 9 divided by 256. I get some decimal, and then I'm going to say convert that to a fraction. Whew, that That's ugly. So now what do I have? I have 2s plus 3/4 divided by s plus 3/16 squared plus 3091 over 1280. So again, if this was a, because this is a real problem, like we don't get lucky and have things just work out really nice. So the point is I got the bottom looking correct. And I guess maybe it's important to notice that on the bottom though, it was supposed to be something squared over there. So in a sense, I'd have to take the square root of that number. So I think I am going to wimp out and use decimals now. I got approximately 1.554. I could have taken the square root, but those aren't perfect squares, so it would have just made it really ugly looking. And then I'm thinking, okay, so the bottom looks correct now. Like that's what the bottom's supposed to look like. Those are both identical. I'm really happy there's a plus sign from the project here. If there hadn't been a plus sign, then I would have had to look down here at arc or hyperbolic sine and cosine, but no wonder I'm living in kind of the real world here. So fortunately it's a plus sign. But then I look on top and I say, okay, well, what do I have to have up there? Well, I got to have exactly 1.554, and I don't have that up there. Or I need s minus, well, exactly what that is. So I need an s, just an s, not 1s, not 2s, not 5s. And then I need exactly what that other number is. And so, how am I going to make that happen? So what I really want to be sitting up here is either 1.554, which is not sitting up there, or exactly that. I wish there was an s plus 3/16 sitting up there, but there's not an s plus 3/16. But the question is, could I get there to be one? Well, notice there's 2 times s up there. And 2 times 3/16 is 6/16 or 3/8. If that was sitting up there, then I could take 2 out of that, factor 2 out, and that would be s plus 3/16. So again, is that up there? No, there's a 3/4. But couldn't I steal a 3/8 from it? So there's supposed to be a 3/4 up there. Well, is there still one up there? Yeah, as long as I guess add another 3/8, because isn't 3/8 plus 3/8 6/8 or 3/4? Okay, so now what do we have? I have this 2s plus 3/8 over s plus 3/16 squared plus 1.554 squared. And then plus the other 3/8 over the top of everything. So basically, this is Laplace transform is not very nice if the problem isn't canned. Well, notice now I can factor 2 out of this, leaving s plus 3/16 there. And now that looks exactly like cosine, where a is 3/16 and b is 1.554. And this was supposed to be, it was s minus, right? So that actually means this is negative 3/16 t, and then the cosine of whatever that other number was, t. I got that in the right form now. Double checking that was a minus sign, right? S minus a, yeah, had to be a minus sign. So I have to think of that as being the opposite sign. Okay, cool. And then The other one is problematic because I really needed a 1.554 up there. And unfortunately, I've got a 3/8. And by the way, this 2 that I factored out still has to be over here. Well, for the second one, couldn't I do the exact same thing? In other words, pull a 3/8 out front, because that's not really what I wish was up there. So great, now there's a 1 up there. But I really want a 1.554 up there. So could I multiply by 1.554 up there? Sure, as long as I also divided by 1.554. So now that looks exactly like the Laplace transform of e to the -3/16 t, but sine of 1.554 t. That's horrible. And of course, I want to switch 3/8 divided by 1.554 to something more decimal-like, which is 0.241. So now I can say that instead of the Laplace transform of y being equal to this gobbledygook, it's now equal to 2 times this plus 2 times that. I can take the inverse Laplace transform of both sides to get rid of them. So y is equal to 2e to the, actually that's just factor the e, since they both have e to the -3/16 t. Let's take it out of both of them, and that leaves 2 cosine 1.554 t plus 0.241 sine of 1.554 t. So I think that's right. So don't do that with Laplace transforms. That's good review, but that was a bad idea. Have to be awesome at completing the square. Man, that would have been so much easier to use the guessing technique. Whew, that was dumb. Hope y'all learned something from that.
Yeah, I remember trying to do something in Laplace transform before, where it was like a decimal problem. I was like, I don't know about this. Maybe I use the other one.
Yeah, you may have noticed on the last test, I worked really hard to make the Laplace transform questions just kind of work out with nicer numbers and factor nicely and so forth, but ooh, that's not good. Well, 9:54. Stay as long as you want, but obviously we're over time as usual.
If you want to do part C of that.
Yeah, so that's worth thinking about. So find the required time to reach the lowest and highest point after that. So if you're allowed to kind of cheat and graph that, and I think I would like to show you this on Desmos really fast. Because remember, I chose to sort of call down positive, so you have to be a little careful with this. So I'm saying I think y is equal to e raised to the -3/16 t times 2 cosine 1.554 t minus plus 0.241 sine 0.554 T. Notice it seemed to like that, but because I pulled it down to, notice it's kind of calling it up to. So in my case, realistically, basically that's the two answers. Like I could cheat and graph them right there. Wasn't that the question I asked? Wasn't it like the highest and lowest or something? Find the time required for it to reach its lowest and highest point after release. But in my case, I might, I might record this wrong. In other words, wouldn't I call that the lowest point? I might, because of my picture, say that's the lowest point and that's the highest point, but that'd actually be wrong because this was actually down and therefore this is up. So actually that's the highest point. So that's the danger of doing what I did. But the cool thing is you can kind of steal it right out of there. Thanks to Desmos. I mean, I guess I would also ask, can you do this algebraically? Can you determine the period of this graph? Because remember that the period stayed consistent. In other words, the distance from here, notice from here it's 0 to, notice it's back to the top at time 4.043. Notice the period's 4.043. And notice it stayed consistent because when I got to the next one, it was 8.068. So the period is apparently 4.043. So you could actually know that ahead of time. I'll show you how you could know it again in a second. And if that's the case, does it make sense this would be right in the middle of that? Since peak to peak was 4.043, then half of that is when it reached down here. So you could actually know what times those were. If you knew the period, then you'd have to cut it in half, but then you could just plug that value in for T. But the question is, how do you find that period? Because looking at your equation over here, what do you do with 1.554? Because that's not the period, or is it the period? Like, what do you do?
Take 2 pi divided by that number.
Mm-hmm. That's exactly right. Well, trying to think of that more complicated. Yeah. So 2 pi divided by that number. And that's on my note sheet if you wanted to go down that road, but it's just kind of cool that you could know that algebraically. So if I take 2 pi and divide by 1.554, look at that, 4.0432. So now then, and I'll do this up here in cheat. If I go back and call this not y, but y of t, and now that I know t is 4.043, then I could just go ask it, what is that? And it didn't let me do that. Why not? Maybe it doesn't like y. Go back and switch it to f. Yeah, that was all it is. So that just gave me that point right there. And of course, all I'd have to do to get the other one is even just cheat and go like this. Say divided by 2. So I'm actually getting, I can get both of those answers algebraically. I guess that's just kind of neat to think about. Isn't that cool?